Cool, cool.
All right, so happy Friday. We are now cruising into June, having a grand old time with differential equations. And what I want to do today is actually show you how Laplace transforms are used. So we discussed Laplace transforms. We saw how we do them, how we calculate them. We talked a little bit about going backwards. And now we're going to tie it all together. So before I dive in, any homework questions, or are we good there? All right, I will take that as we are good. All right, so, the homework for Monday was really easy. Yeah, it's a bunch of algebra. It's not that big a deal. Oh, and you'll also notice that I put a whole bunch of homeworks up. I think I gave it all the way through chapter 8, maybe even some chapter 9. I don't even remember how far I got, but anyway, you're good to go. So let me show you the whole point of the Laplace transforms, okay? Because like, yay, we created them. We saw that they were linear operators and blah, 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 blah. Well, let me show you how this is going to work out for us. So let's take a differential equation that we definitely know how to solve. All right, this one's super easy. This is not one that I would ever recommend using the Laplace transform on. So if we've got y double prime minus y prime minus 2y equals 0, you know exactly how to solve that. In fact, I bet a lot of you could tell me the solutions right now. Right? But let's make this an initial value problem as well. So I'm going to also put on here that we're going to have y of 0 is equal to 1, and y prime of 0 is equal to 0. So again, if this was like question number 1 on the final exam, you'd be super stoked because you could just fly right through it. No big deal. All right, well, let me show you how the Laplace transform works out. So Laplace transform is an operator. It's a linear operator. So what we're going to do is the same thing that we always do, which is when we have equations, is let's do the same thing to both sides. Let's actually take a Laplace transform on either side. Okay, so the linearness of this operator is going to let us do this on the left-hand side. So we'll have the Laplace transform of the second derivative minus the Laplace transform of the first derivative minus 2 times the Laplace transform of the function itself. And then that's going to equal the Laplace transform of 0. Now, I don't think we actually ever calculated the Laplace transform of 0, but I think it's probably easy enough for you to see that it equals 0, right? Because remember what we do, we take e to the minus st times the function. Well, if we multiply anything by 0, we get 0, and then integrating 0 also gives us 0.
Doesn't it have to map to 0 always if it's a linear transformation?
Oh yeah, there's that too from linear algebra, right? 0
Yeah.
has to go to 0. All right, so it actually would not be c because it's a definite integral. Remember, we have bounds on it. The integral goes from 0 to infinity. So we will get a number, which in this case is 0, as Thea reminded us that has to happen. All right, so now's where we're going to use that fact that we came at last time, that theorem about the derivatives. So if you go back and you look, you'll see that we know, like, for the second derivative's Laplace transform is actually equal to s squared times the Laplace transform of the function itself minus s times the function evaluated at 0 minus y prime at 0. So those three, these guys all came from that. So that was actually a corollary to the theorem. Hopefully you remember that from Wednesday, or can go back and look and see where it came from. Okay, So now let's keep going. We also then have minus the Laplace transform of y prime. Okay, well, that one similarly, we can use what we developed last time, which shows us that that's s times the Laplace transform of y minus y of 0. So those two pieces that came from this. And then we still have the minus 2 Laplace transforms of y equals 0. All right, so let's stop and kind of talk about the why, right? Why did we just do this? Well, look at what we have now. We got a whole bunch of Laplace transforms, but they're all Laplace transforms of the original function. Everything else are things that we know. Y of 0, y prime of 0, those were from our initial conditions. So let's put those in, and let's just see what happens here. So we're going to get s squared times the Laplace transform of y minus s, because y of 0 was 1. We're going to get minus 0, because y prime of 0 is 0. And we're going to get minus s times the Laplace transform of y plus y0, so plus 1, minus the 2 Laplace transforms of y. So our initial conditions took care of all that other stuff. And what I can do now is actually solve this thing for the Laplace transform. So I'm going to write this as L of y equals. So let's move some stuff around. So I'm going to factor out the Laplace transform of y. So we get the Laplace transform of y times s squared minus s minus 2. Okay, so that was those three pieces. And then this is going to equal s minus 1. So I'll go ahead and fire those other things onto the other side. So all I have to do is divide by that factor. And now what we know is the Laplace transform of the solution. So now we'll go ahead and go back to what we were talking about last time, which was given a Laplace transform, you can actually go backwards, right? Because it is a one-to-one function, or operator, I mean. So let's see if we can figure out what y is going to look like. So let's do what we always do with these, which is let's start by factoring the bottom and then see what we can do about splitting it apart and all that good stuff. So this is going to be s minus 1 over s minus 3, or how about s minus 2, times s plus 1. And now let's do the partial fractions. Let's split this apart. So we're going to have a over s minus 2 plus b over s plus 1. So if we were to get a common denominator, that tells us that a times s plus 1 plus b times s minus 2 has to equal s minus 1. So let's just plug in some values. Like if we let s equal -1, then the a goes away, and we're left with minus 3b equals minus 2, or b is 2/3. And then similarly, if we let s equal 2, we're going to get 3a, the b bit goes away, equals 1. So a is 1/3. All right, so what that tells us then, I'm going to change color just so we can see it a little bit better. Laplace transform of y then is going to be 1/3 times 1 over s minus 2 minus, or sorry, plus 2/3 times 1 over s plus 1. All right, so now let's go backwards. We need to think about what function gives us a Laplace transform of, say, 1 over s minus 2. What gives us 1 over s plus 1? So we can use our chart. And I don't know if you guys noticed, but I did put a link, a file on the Canvas site. If you go over there and you look in files, you'll see that there's one that's called like Laplace Transform or whatever. Okay, cool.
Yeah,
you put one up in Discord as well. So
yeah.
Okay, cool. So we can make use of that, but remember that constants, those are just constants, so they show up. So this gives us y equals 1/3, and then 1 over s minus 2, that's the same as e to the 2t. And then the other one, we're going to get plus 2/3, and the 1 over s plus 1 is the same as e to the negative 1t. And so there you go. There is the solution to this differential equation. Now, like I said, we already know how to do that. We wouldn't have done it this way because you would have seen the fundamental set pretty quickly as e to the 2t and e to the minus t when you did the algebra. And then you could have just done, create your system of equations to find the coefficients. But I think this helps illustrate how this works on something that we know what the answer should be, so we can see that it actually plays out. Now, where this is going to come in handy is when it's not so obvious what the solutions are, right? Up to this point, we've had nice and easy things, but you can imagine that if it gets kind of gnarly, this could be nice because it was all algebra. We didn't do one step of calculus. I don't know if you realize that. Everything we did from the original differential equation to getting to the answer required exactly 0 calculus. Well, not exactly, because the calculus happened earlier, right? But once we did the calculus once, this turned into algebra. And I think I mentioned this last time, that that's kind of the point of this, is it makes it an algebra problem, which I know for some of us means it's going to be horrible. But really, if you think about it, algebra is preferred because it's easier than calculus. All right, so what do you guys think? Not too bad, right? All right, so let's make it a little bit more complicated. Just a little. We're not going to get too crazy with this stuff yet. So let me change this differential equation so that it's not homogeneous. Because as soon as it's not homogeneous, we know that that requires a bit more work when it comes to solving them, even the ways that we already know. So let's do this. Let's change this to y double prime plus y equals sine of 2t. Now, this is another one that you know how to do. You would find the solutions to the homogeneous to create your fundamental set. And then you'd have to do some sort of undetermined coefficients or variation of parameters or some such thing to figure out a particular solution. But let me show you that we're actually going to get the solution that we would have found otherwise by doing only algebra. But again, I need to give you some initial conditions. And I should probably write this on the board just to kind of reinforce it. But the only time that Laplace transforms is going to be useful is when it's an initial value problem. Okay, so let me just write that right here for a second. So we only use these guys with initial value problems. You may remember that when we turned it into the algebra, excuse me, we had a whole bunch of those, y of 0, y prime of 0, stuff like that. If it's an initial value problem, then we know those numbers, we can plug them in and life is good. All right, well, let's try this on this guy. And let's see how it goes. So we're going to take a Laplace transform of both sides. All right, so just like before, let's take a Laplace transform. So you notice that we've got the y double prime. So that y double prime is going to do what give us what we gave before, which is going to be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. So that's the Laplace transform of y double prime. Then we need to add to that the Laplace transform of y. So this is very much like what happened last time. It's just we don't have a y prime that we were doing the Laplace transform on. But now we have to worry about what's the Laplace transform of sine of 2t. So this is where our chart's going to come in handy.
It's going to be 2 over s squared plus 4.
Good. So this is going to equal 2 over s squared plus 4. Let me write it over here. It makes you see the equal maybe a little bit better. And so this is just the form for sine of at. The Laplace transform of sine of at is a over s squared plus a squared. All right, well, we're going to do exactly what we did last time, which is let's solve this for the Laplace transform of y. So let's factor out all the stuff that's on the Laplace transform of y. So we got Laplace transform of y times s squared plus 1 minus 2s minus 1 equals 2 over s squared plus 4. So Laplace transform of y is going to equal, or times s squared plus 1 is equal to 2 over s squared plus 4 plus 2s plus 1. And I can combine this together and then divide by the s squared plus 1. So we get the Laplace transform of y is equal to 2s cubed plus s squared plus 8s plus 6, and that's all over s squared plus 4 times s squared plus 1. All right, so any questions on the algebra before we go and figure out what this function is? All right. So this, of course, means time for partial fractions. Okay, now I know that we, in this class, haven't done partial fractions on something like this. Do you remember what you do when you have quadratic factors instead of linear factors?
Don't you tack on an extra term multiplied by the variable, and then scale that up every time, every successive power that you have?
Okay, I think you're thinking about what we did when we were looking at undetermined coefficients.
Oh,
when you have the repeated root.
Yeah.
Yeah, so this is slightly different. This is more of a algebra question.
Got it.
Actually, go back to second quarter calc. Okay, well, here's how this plays out. What we're going to want is a fraction whose denominator is s squared plus 4, and another one whose denominator is s squared plus 1. But what we put on top of those are linear pieces. So when your denominator is just a linear polynomial, so first degree, then you just put a constant on top. But if it's a quadratic, you put a linear on top. And I'm curious if maybe Thea, now I think about what you said, maybe you were thinking about if you have a repeated factor down here. Because like if you had, say, s plus 1 squared, you'd have a fraction a over s plus 1 and then b over s plus 1 squared. So you're on mute, can't hear you. All right, so let's take care of this then. So we'll do the same thing that we always do, which is get a common denominator and set that equal to this top. So we're going to get as plus b times s squared plus 1 plus cs plus d times s squared plus 4. And then we need that to equal 2s cubed plus s squared plus 8s plus 6. All right, now these are much less nice when you've got the quadratics that are on the bottom, because there's not a nice number to plug in for s to make things go away. You pretty much just have to plug in 4 different s's, or alternatively, and that's what I'm going to do here, is group everything by the powers of s. So like if we were to distribute through, what we'd see for our s cubes is we would get a plus c times s cubed. For the s squareds, we're going to get b plus d. For the s's, we're going to get a plus 4c. And then for the constants, we're going to get b plus 4d. And so now we can go ahead and just equate those to the coefficients. So we get a plus c equals 2, b plus d equals 1, a plus 4c is equal to 8, and then b plus 4d is equal to 6. So then solving this gives us a equals 0, c equals 2. So from these two guys. And then from the others, we get b is equal to, or sorry, d is equal to 5/3. So b is equal to minus 2/3. So a whole crap ton of algebra. But now we can plug those numbers in for a and b and c and d. And so this is what our partial fraction decomposition is going to look like. We're going to get minus 2/3 over s squared plus 4 plus 2s plus 5/3 over s squared plus 1. Okay, so I just literally plugged in all those numbers in for their respective a, b, c, and d. So we're almost ready. Let's split this up even further. Like break this second one into the two pieces, one with the 2s on top and the other with the 5/3. And so where we end up with, or end up at after doing that, Laplace transform of y is going to be minus 2/3 times 1 over s squared plus 4 plus 2 times s over s squared plus 1 plus 5/3 times 1 over s squared plus 1. And now all of those are in a form for us to try to figure out. All right, so let's do it. Let's look at our list, figure out what the what this y has to equal.
So the first term is going to look like sine of AT.
Okay, so again, that's much like that form we just saw.
Yep.
Right. The for sine of AT, it's a over s squared plus a squared.
Mm-hmm.
So what we'll do, let's take that 2 and actually bring it in there so that that's exactly of that form. So we're going to get y is minus 1/3 sine of 2t. All right, how about the next piece? The 2 times s over s squared plus 1.
That's just going to be cosine t.
Okay, good. So for cosine of AT, right, we saw that how that relates to the sine of AT is that there's just an s on top.
Yep.
Right, so this is going to give us then plus 2 cosine of t. And then what about that last one?
Isn't that just sine of t?
Yeah, that's just sine of t, because again, sine of t, a is equal to 1. So we get sine of t. So in terms of what the solution is then, we've got minus 1/3 sine of 2t plus 2 cosine of t plus 5/3 sine of t. And so these last two, the cosine and the sine, those were the fundamental set that you would have found if you had made the polynomial. This polynomial would have been r squared plus 1, gives us r is plus or minus I. So we know sine t and cosine t are those two. And then the 2 and the 5/3 would have come from doing the initial value problem. And then the minus 1/3 sine of 2t, that's our particular solution. And we would have made that guess if we had gone to our undetermined coefficients. Since it was sine of 2t, we'd make a guess of a sine of 2t plus cosine of 2t, or b cosine of 2t. And then that would have spit out b equals 0 and a equals minus 1/3. All right, but again, notice exactly this much calculus. And if you're not looking at the screen, 0, right? We did no calculus here whatsoever, and yet we were still able to get the solution to this differential equation. So yeah, we trade calculus for algebra, which on some days is good, on some days not so good, but there you go. All right, so this is the whole point of using Laplace transforms, but it still isn't the full story, because clearly the ones we've done so far are not that big of a deal. So what if I just change it to this guy? So not a terrible differential equation. Let's go with y double prime minus 3y prime minus 5y equals, okay, so it's starting off nice and easy. You know what to do. You make your polynomial. You can find your fundamental set. Everything's great. But what I'm going to do is I'm going to set this equal to f of t. But here's what f of t is. f of t is a piecewise defined function. So we're going to force it. We're going to have a forcing function here, but this time the forcing function is piecewise. So first, why are we talking about this? Other than the fact that we can, right? Because math is math. But can you see a real reason why maybe this f of t is piecewise?
Not everything in the real world follows a nice, tidy graph.
That
and it
is
can be
100%
piecewise.
true, right? And so sometimes we need to have a define it in slightly different ways. But even more, think about what that f is in an applied situation. Like a lot of the applications we saw, think, like spring mass systems and the RLC circuits. That's our forcing function. That's the external force.
Got it.
And how often in the real world does the external force change? Pretty much always.
Yeah.
Right. And that definitely backs up what you were saying, Thea, about the, in the real world, things aren't nice. And, even if we talk about a circuit, right, well, we plug it in. So we get a forcing function that's sinusoidal, but then maybe we unplug it. Or if you want to talk about a spring mass system, maybe there's, all of a sudden a fan gets turned on. And then we turn the fan off. Next thing you know, that's a different kind of function, right? So it needs this piecewise definition. All right, so the question is, can we still do the Laplace transform of something like this? Is it possible? Because if it is, then cool. We can just do it and do what we did before to solve. So let's spend some time talking about finding Laplace transforms of, say, piecewise functions like this. All right, so here's really what I want to do. Let's not worry about the differential equation. Let's just worry about first finding a Laplace transform of this. So here's a piecewise function, and let's find it. So if you go back to the definition, right, this is the integral from 0 to infinity of e to the minus st times f of t. And if you were to look at this, you would see that since it's piecewise, we really need to break this integral into two chunks. There's going to be an integral from 0 to 1, and then the one from 1 to infinity. So yeah, Wes, I just saw that you typed that in. That is exactly what we'll do. Because it's a completely different function in those cases, what this would break down to is the two integrals, the one from 0 to 1, and then the other from 1 to infinity. Okay, so let's go ahead and figure out what those are. It's really just a question of getting those two different integrals and adding them together. All right, so for the first one, if we integrate e to the minus st and we go from 0 to 1, all right, so what we end up with is 1 over s minus e to the minus s over s. So you may remember that the Laplace transform for 1 is just 1 over s. That's this piece. But we don't get the entire of the 1 over s. We also have to take this other piece away because it's not going to infinity. Normally that runs off to 0. Okay, so now let's go ahead and find the integral for the other one. So we're now going to have t squared times e to the minus st. And this time we're going from 1 to infinity. Ooh, my T89 didn't like that. It says it's undefined, but I know it's not. So let's be smarter than the T89. We'll just get with the what the form is, and then we'll plug in the 1 and the infinity. So we get a negative t squared s squared plus 2ts plus 2 all over s cubed. And then that's times e to the minus ts, or minus st, I should say. Same, but let's be good about it. Going from 1 to infinity. Okay, well, obviously plugging in the 1 is easy. We plug that in for t. Let me just start writing out what we got. So those are the first two pieces. Then for this one, when we plug in 1 for t, or yeah, for t, we're going to get s squared plus 2s plus 2 over s cubed times e to the minus s. It's a plus now because we're subtracting the negative. Okay, and then the other piece, as we let t go to infinity, that e to the minus st, well, that's just going to get incredibly tiny. And it's going to actually grow a lot faster than the s squared that we've got on top. In fact, even if you just look at this guy, or the t squared, we've got an infinity squared over e to the infinity. And you do a L'Hopital's rule on that a couple times, you see that drops to 0. All right, so there is our Laplace transform of that piecewise defined function. So it's definitely doable. Right. So did Symbolab do it for you, by the way? Did you try that, Wes? I'm just curious because like my T89, when I tried to do that infinite, yelled at me and it said undefined.
I plugged it into Symbolab and I got the same. I didn't get a undefined answer.
Okay, because the issue, of course, is I think the issue with the T89 is the S.
Yeah.
Because it doesn't always converge, right? If S had been negative, that would have given us an e to a positive, which then would have caused it to blow up. So I think that's the problem with sometimes with the technology with Laplace transforms. Although I bet there are actually internet resources that take Laplace transforms for you. You just type in the function and it spits out your Laplace transform. So, but regardless, we're able to get it. But I do want to rewrite this just slightly, just to show you, well, that kind of highlights something. Notice that there's a whole bunch that has an e to the minus s in it. So I'm going to pull that stuff out and just kind of separate that. Okay, so if I factor out the e to the minus s, and then of course I can go ahead and combine these two, but notice the minus 1 over s is the same as minus s squared over s cubed. So those would go away. So we're left with 1 over s plus 2s plus 2 over s cubed times e to the minus s. All right, so no big deal, right? I mean, yeah, it's a big deal because it's kind of a pain in the butt, but tackling these are not a problem. You just break your integral up into the different pieces. Like if this had been a 3-piece piecewise defined function, you would have had 3 integrals. Like let's say it was, from 0 to 1, 1 to 4, and 4 to infinity, or what have you. Okay, so we can do it. We can absolutely do it, which then of course means we can attack these problems using Laplace transform. So if you go back to that original differential equation I gave you, now we've got the Laplace transform of the right-hand side. We do the Laplace transform of the left-hand side like we always do, solve for it, and then do inverse and yada, yada, yada. Okay, so honestly, this is the big place where we use Laplace transforms. Because think about what your option would be otherwise. Otherwise, you'd really have to solve 2 different differential equations with 2 different initial conditions, right? Like this one, I don't remember exactly what I gave you, so if it's not exactly the same, then I apologize, but I think it was this, right? Alternatively, what we could do is actually solve these 2 independently. And if I gave you initial conditions, and again, I don't think I did, but let's just say that I told you something like this, right? That y of 0 is 1 and y prime of 0 is 1. That's definitely enough for us to figure out this first one. But do you see what the problem is trying to go about it this way? And for sure, it's not the first differential equation because we got plenty of information. Like, what do we always need if we're going to do a Laplace transform problem?
Initial conditions.
Initial conditions, and we don't have initial conditions for the second one. Now, we could find them, right? After we solve this first and we get the function that describes it, we could then plug in t equals 1, figure out what that point is. Well, that's an initial start for this guy. And then we could take the derivative, plug in 1. That'd be the start for this. But notice that this now requires a lot. It's basically 2 different Laplace transform problems. And one of those, we don't even have the information that we need. We're going to have to build it ourselves. So it is going to be in our best interest to tackle them as piecewise functions and do the Laplace transform. All right, well, I want to show you something else that's actually going to help us with this Laplace transform stuff. I'm going to write this down on my board below my line so I don't erase it, just to remind us what that Laplace transform was equal to. Because I want to relate back to it. Okay. Yeah, I could have all kinds of fun stuff written down here, right? Like, as far as you know, if I can't pan the camera down a little bit, it says something like, Wes is a goofy 4-eyed freak or something like that, which I would never say. Well, no, I would. I'd say it to your face, except for the 4-eyed thing, because I'm there with you. But, Right, so who knows what I've got written down there. Anyway.
Speak for yourself, Bruce.
You know I love you. Okay, let me introduce you to another function. And this is called the step function, or the unit step function, or the Heaviside function. It actually goes by many different names. but we'll start. This book calls it the unit step function. But I do want to mention this. It's AKA the Heaviside function, named after a mathematician. Only reason I'm mentioning that is I will routinely call it the Heaviside function. So I want you to know what I'm talking about. Okay, so the unit step function, super easy. U of t, it's a piecewise function that's either 0 or 1. And where it switches is at 0. Okay, so the unit step function is 0 when t is less than 0, and 1 when t is greater than or equal to 0. So this is why it's called the unit step function, because it just goes up 1 from 0 to 1. You can also shift this. And what this is going to look like, it's the same, 0 to 1, but now it's going to be when we're less than c versus greater than or equal to c. So basically, this just allows you to make it do the jump wherever you want. You just shift it accordingly. Now, I'm going to use a slightly different notation than the book, because I don't like writing all of this u of t minus c business. All that really matters is that it's u, and then where the c is. And so what you'll see me write is u sub c of t. Basically, it's saving me the stroke of writing a minus, which if you know anything about me, oh, that's always worth it. One less thing to write. Okay, so this is actually what I'm going to write when I talk about the unit step function. When it's shifted, we'll just specify where we are. If you don't see the c, it is 0. It's implied that it's 0. But other than that, I will put what the c value is. Okay, so no big deal, right? Super easy. So let's actually look at what the Laplace transform is for a unit step function. And I'm going to go ahead and just do the generic where it's been shifted to wherever at c, because then, of course, we know what it's going to be at 0, right? We can plug that in. All right, so let's find the Laplace transform of it. So we'll just go back to the definition. It's integral from 0 to infinity of e to the minus st times u sub c. So it's going to be 0 all the way up to c, and then it's going to turn into a 1 when we get to c. So we could, and we will, let's do the same thing that we did before, which is break it into the two pieces. So there's going to be the integral from 0 to c of e to the minus st, plus the integral from c to infinity of e to the minus st times 1. So this first part, of course, since we're multiplying by 0, just gives us 0. So that doesn't even matter. And then the other one, we just need to integrate e to the minus st. So that's going to give us a minus 1 over s e to the minus st, evaluated at c and infinity. The infinity is going to drop to 0, as we've seen countless times. And then the c, we're going to get e to the minus ct, or sorry, cs, over s. And like always, we really should write as long as s is greater than 0. So this piecewise function is actually really, really easy to get. It's just e to the minus cs times s. All right. So far so good? Yay? All right, now I want to show you how we can use this unit step function, or this Heaviside function, to actually write piecewise functions in a slightly easier way. So let's do this. We'll just take baby steps here. But let's say we've got a function f of t that is 0 when t is less than 4, let's say. And it's equal to t plus 1 when t is greater than or equal to 4. Okay, now if this had been just 1 instead of t plus 1, that's exactly u4. But it's not. We actually do get t plus 1 instead. But here's what's beautiful, is we can actually write this as u4 of t times t plus 1. Because think about what u4 did. It's 0 up until 4. Okay, so 0 times anything is 0. And then starting at 4, it's 1. So 1 times t plus 1. That gives us 2. So check it out. This is how I like to think about u4, or u sub c. This is the switch that turns on at 4. Like literally, that's what UC does, is it turns on whatever this function is when you hit C. So any piecewise function can actually be written this way, even if it's not necessarily 0 and 0. So let me show you with one that's the one that we did just a minute ago, where it was equal to 1 and then t squared. All right, so let's do that guy. Let's take f of t equals, so we're going to have 1 and t squared. And I had them turn it 1, right? At least that's what I'm going to go with. All right, so let's do the same thing, and let's write it in terms of the unit step function. In this case, it's going to be u1. Okay. But first things first, notice that we're not starting at 0. We're starting at 1. So that means my function is equal to 1 until I flip the switch at 1. Okay, so whatever your first piece is, just use that. Okay, so this is going to be 1. Then what I'm going to do is I'm going to turn something on at 1. So I'm going to use the step function at 1. And now I'm going to multiply it by something else. So what am I going to multiply it by? Okay, so this one's kind of a trick. Because you might go, let's just do t squared.
Yeah, but it's the top portion of the piecewise function that's like weirded me out.
Okay, and it should. Had this been 0, then u1 of t times t squared, everything's great.
Yeah.
Okay, but here's the problem. Like if we just did this, what would happen at 1? Well, at 1, this would turn on, but we would still have this 1 out front. So we'd actually have 1 plus t squared. That's a problem. So what we're actually going to have to do is turn on t squared minus 1. So like I mentioned, this is a switch. Here's how I like to think about it. So it turns stuff on when it's positive, and it turns it off if you subtract it off. So this piecewise function can actually be written as 1 plus u1 of t times t squared minus 1. So it's all about paying attention to what's getting turned on and what's getting turned off. And what's really beautiful is even if this had like 4 pieces, we could still do same sort of thing. So let's do one more here. Let's make this one kind of big and ugly looking. Well, let's say we've got f of t equals sine of t, e to the t, t squared, 0. And this will be for t less than, say, pi. This will be for t's between pi and, let's go, 6. This will be for t's from 6 to 10. And then nothing from 10 on. All right, so let's see if we can build unit step functions that will do this for us. All right, so here's where we start. We start with whatever the original function is, sine t. Okay, but now we need a u sub pi, because pi is where we're going to start doing new things. All right, so in terms of what goes in here, we're going to say, what do we need to turn on? Well, we need e to the t to turn on. So we'll put e to the t. But then we need sine of t to turn off. So I'll do minus sine of t. All right, and then the next place that things are going to change is at 6. I need t squared to turn on, so I'll have a t squared. And then I need e to the t to turn off. So I'll subtract e to the t. And then lastly, we need to have a u10. And again, what do we need to turn on? Well, nothing. But what we need to turn off is t squared. So we'll put a minus t squared. So that's how we'd represent that piecewise defined function using just the unit step function. All right, so again, yay, we can do it, big deal. So why do you think I'm spending our time looking at how we can reconstruct these in terms of the unit step function?
This is useful in a applied setting.
Yeah, and really it's going to be with Laplace transform.
Yeah.
Because again, what if I want to take the Laplace transform of this right-hand side?
Yeah.
Okay, I can do it as 4 separate Laplace or 4 separate integrals and do all that. Or if I know how to tackle something like this one, the Laplace transform, it's a linear operator. So I need the Laplace transform of sine, no problem. If I know how to handle a form like this, boom, I've got Laplace transforms of those other three, and it's fast. It's really, really quick. Okay, so that's why we care about this, is so that when it comes time to do the Laplace transform, this will be fast. And I promise you, if you look at a table of Laplace transforms, either the one that I put up on Canvas or the one that Thea shared in your group there, I promise you that there is something that shows the Laplace transform of a unit step function times some other function. So once we develop that, it's going to be really easy for us to go backwards. Okay, but I think I'm done for today. I've done enough algebra to make your brains mush. So we'll go ahead and stop here. But on Monday, we're going to look at, all right, how do we do the Laplace transform of the step function times something? And then we'll see how we can use that to help us go backwards when we end up with a Laplace transform like we did that came from a piecewise defined function. Okay, so we'll go ahead and pause here.